Everyone, this is 10.4 where we discuss areas and lengths in polar coordinates. Now, of course, to discuss the area in polar coordinates, it'll involve an integral, but to actually see what the integral is, we first have to start off with something a little more simple, and we need to recall what the area of a sector of a circle is from trigonometry, or I guess geometry, and it's basically this. Its area is equal to theta over 2 times r squared, where theta, of course, has to be in radians. And if you kind of think of a full circle, its angle is 2 pi. 2 pi over 2 is pi, so you get pi r squared. And that is indeed the area of a circle, and any other portion of an area of a circle, or of the circle, would be the area of a sector, and its area would then be whatever portion of that angle multiplied by 1/2 r squared, kind of like how the angle for the full circle, 2 pi, is multiplied by 1/2 r squared. So you get this basically because every sector is just a portion of a larger circle. So something to keep in mind. But theta has to be in radians, okay, so keep that in mind. Also, a better way of writing this for our purposes is 1/2 r squared times theta, and you'll see why in a second. So what we're going to do is the following. We're going to estimate the area of an enclosed region. So the region is going to be enclosed by the curve r equals f of theta. So this curve right here in polar is r equals f of theta. Between the values theta equals a and theta equals b. So theta equals a is this line, theta equals b is this line. So we're kind of imagining the angle swooping up from here to here. So this first angle is theta equals a, and the second angle here is theta equals b. Right? So the region we're trying to estimate is this region in between. I'm not going to shade it quite yet because I want to draw some sectors that'll estimate it. So now we're going to break the region into n subsectors. So sector, again, a sector will look something like this, just a portion of a circle with radius r and angle theta. So the area of this region is that. And once we break it up into those small n many subsectors, we'll label each angle as delta theta. So we're trying to do basically what we do for area under the curve with rectangles, all with the same width. Here they'll all have the same length. If you recall, for area under the curve, the width would be delta x. Here all of the lengths are going to be delta theta. And we're going to label then their radius as ri. So basically, this will have an angle of delta theta. So let me just arrow to it, delta theta. And then this sector here, well, let's imagine that let me do that a little better. Let's imagine they're all uniform, right? We want the angles to all be the same. Looks a little better, I guess. And then the next one will be over here, and so on. So you kind of see the idea. We're just estimating the area under the curve as you would in Cartesian with rectangles, only since it's in polar, we have to abide by the polar rules. In other words, we have to go by angles, so therefore we have to have sectors from the origin. So this is basically what we're doing. And what we'll discover is this. The area of this enclosed region will just be the limit as n goes to infinity of the sum from n equals 1. I guess it would be I equals 1. Because our index is I, so we end at n. There we go. Of the area of each of these. And the area of each of these is just this. It's 1/2 r squared theta. Now, of course, the r's we have for each one is r sub I. So we're summing through each of those squared. And the angle for each of them is delta theta. Now, of course, really what this is just an integral. This is literally a Riemann sum, which we can write as an integral between the angles a and b of 1/2 r squared d theta. Of course, ri is f of theta I. So this should make a lot of sense. And this r squared is the same as f of theta squared. But we like writing r squared. We just remember that it's r is theta squared, is f of theta. Kind of like how y is f of x. Okay, so this is the area we'll be using. There are the area formula we'll be using, that is. There are a few big points I want to point out, and I want to say that we want theta to go from A to B. So we want A to be less than B. Okay, that's actually very important. We also want to try to have A and B be contained in the interval 0 to 2 pi. Sometimes you don't have a choice, and we'll see examples of that shortly, where let's say you're between the fourth quadrant and the first quadrant, you have to go from here to here. You have no choice to either dig into numbers below, or I guess theta values below 0, which are negative, or for theta values above 2 pi, which would be, well, just these ones here in the first quadrant. Sometimes you don't have a choice but to do that. And again, we'll see examples of those. But for the most part, this is what we want to have happen. So I don't want to put an exact restriction on this, but I want to say that this is what we kind of aim for. And then if we're in a sticky situation where we have to go beyond this interval, we certainly can. Anyways, let's take a look at a few examples. All right, so for this example, we'll be finding the area enclosed by one loop of the four-leaf rows r equals cosine of 2 theta. Now, if you graph this, you'll actually see what the image looks like. But if you try to do this without graphing, it's actually pretty difficult to do because you have no idea what actually is going on. The best thing is to graph, and in fact, that's something we'll see a lot in this section. And we kind of saw it in 10.3 actually. Polar coordinate curves are very visual. You have to have some visualization. You have to graph somehow, whether that's using a graphing utility or sketching the graph by using a table, which is not recommended because it takes too long. But I'm going to try my best to explain what's going on without graphing first, and then we can kind of look at the graph and see what's going on. So first off, what does it mean by one loop? Well, when I think of a loop, you have this kind of image here. Now, the other thing is it's not clear if this happens at the origin or not, but I'm going to tell you that it does. Now, if you know what a rose looks like as far as math goes, a rose is some type of shape that it has these loops like this. And they're usually centered at, that's a pretty bad drawing, but they're usually centered at the origin. Now, it is possible that you have a drawing like this, or a curve like this, where you have this type of shape where you have these loops, and it's not centered at the origin, so each loop doesn't happen at the origin. So it's really difficult to actually figure out what's going on. But if you have the intuition that the loops pass through the origin each time, then we can get something going actually. Because if you set r equal to 0, that's where it passes through the origin. So if we had that additional bit of information, then we could actually find out where each loop occurs by setting r equal to 0. So in other words, if you solve this equation here, well, first off, cosine is 0 at, well, let's see. Cosine is 0 at pi over 2 and 3 pi over 2. So we want 2 theta, the inside of cosine, to be pi over 2 plus a multiple of 2 pi, or 3 pi over 2 plus a multiple of 2 pi. Now that multiple of 2 pi part is actually pretty important here because of course we're going to divide by 2 to get theta by itself. So that means when you do that, you get pi over 2, well I guess pi over 4 now, plus that divided by 2 is pi k, that's a plus. And similarly here, this is 3 pi over 4 divided by pi k. Now remember that what we want for our theta values, like I mentioned previously, are to be in between 0 and 2 pi. So this is in the first quadrant and 3 pi over 4 is in the second quadrant. When you add pi to pi over 4, you get in the third quadrant. When you add pi to 3 pi over 4, you go from being in the second to being in the third because pi is, of course, a 180 rotation. So in essence, you get this when you stick to being in between the values 0 and 2 pi. You get pi over 4, 3 pi over 4, pi over 4 plus pi, which is 5 pi over 4. And then finally 3 pi over 4 plus pi, which is, I guess, 7 pi over 4. And this is it. These are the only values that are in between 0 and 2 pi. Now, obviously, there are more values if you go beyond 2 pi and more values if you go below 2 pi, below a 0. But yeah, so anyways, these are the values where we pass through the origin, meaning that there are a total of 4 loops. Makes sense because it's a 4-leaf rows. So the image actually will look something like this. Okay, now each one of these loops occurs at a given angle. So there's so many ways to tackle this, and we only want one of the loops. But the problem is, how do we know they're all the same size? We don't. That's another thing we have to kind of assume. But I can kind of share with you and give you a little bit of intuition that they are by just trying each of them. I'm not going to do that, but I'll kind of give you another option as well that'll allow you to see that that is indeed true. Now, this obviously is an example from the book, and what the book does is they go from theta equals negative pi over 4 to theta equals positive pi over 4. And I'm tempted to do that, but I don't want to, because what's the problem here? The problem is that negative pi over 4 isn't any of these values. It's actually below 0. But notice that this is also the same as a line theta is equal to 7 pi over 4. Now here's a problem. This is why I bring this up. If you go from 7 pi over 4 to pi over 4, swooping like this, remember we want a to be less than b. Since a is bigger than b here, there's a huge problem. And the problem is this. If you take the integral from 7 pi over 4 of something to pi over 4 d theta, the huge problem here is that this is the same by rules of integration. It's equal to negative the integral from pi over 4 to 7 pi over 4 of the same integrand d theta. Now why that's a problem is that here we have the intuition that going from 7 pi over 4 to pi over 4 will actually grab one loop, but it doesn't. What this tells us is it actually goes counterclockwise in this direction and will give us a negative value actually. So you have to be a little careful. This is going to give you something completely different, because going from pi over 4 to 7 pi over 4 will clearly capture these three loops, and then going from 7 pi over 4 to pi over 4 should give you, well, the same area, but it'll be negative because you're going backwards. So just kind of keep that idea in mind. And this is the main reason why we want a to be less than b. So you have two options. One option is to make the smaller one that we want to be smaller, so the starting point, make it smaller, so that forces it to be below 0, negative pi over 4. Or we can say stick with 7 pi over 4 and make this be, well, what pi over 4 is equivalent to above 7 pi over 4. So it'll be obviously bigger than 2 pi, and in fact it'll be 9 pi over 4. And this actually works. So if you do either of these two, so going from negative pi over 4 to pi over 4, or from 7 pi over 4 to 9 pi over 4, you'll actually get the same area for this one loop. But again, just because I don't want to do that, and the book kind of does it for us already, I'll just do the top one to play it safe. But I'm just mentioning that kind of like I guess I foreshadowed earlier. But I'm going to go instead from pi over 4 to 5 pi over 4. And yeah, so I want to find the area of this one loop here. So I know my bounds. I know the limits of my integral. And do I know the inside? Well, yeah, I know the inside is going to be 1/2 r squared d theta. So I'm going to erase this and write that. So first off, I misspoke earlier. I wrote a 5 pi over 4. I really meant to say 3 pi over 4. 5 pi over 4, by the way, is here in the third quadrant. But now that we have that settled, let's move on. So the area is going to be, according to our formula that we previously saw, the integral of 1/2 r squared. Now remember, r squared is just cosine squared of 2 theta. So this is 1/2 cosine squared of 2 theta. And our bounds are pi over 4 to 3 pi over 4. Like that. Now, of course, the 1/2, yeah, we can pull outside of the integral because it's a constant, of course. The bounds are still the same, pi over 4 to 3 pi over 4. And how do we handle cosine squared? Well, if you recall from, I guess, 7.2 a while ago, we have to use power reducing formula. And we can write this as 1/2 times the quantity, let me write it like this. 1/2 times the quantity 1 plus cosine of what? Cosine of the angle doubled. Now here the angle was 2 theta, so when you double 2 theta you get 4 theta. So power reducing reduces the power, but it doubles the angle, of course. It's kind of equivalent to the double angle formula, actually. And then d theta. Now pulling this 1/2 out again and joining it with this 1/2 gives you 1/4. And then if you actually antiderive these just straight up, antiderivative of 1 is theta, antiderivative of cosine is just positive sine. Since it's a 4 theta, we have to divide by 4 with that term, basically by the chain rule, and then evaluate this between the bounds of the integral, pi over 4 and 3 pi over 4, and then afterwards multiply by the 1/4 on the outside. Okay, so let's see what happens. So let's plug these things in. So plugging in 3 pi over 4 gives us 3 pi over 4 plus 1/4 sine of, well, 4 times 3 pi over 4 is just 3 pi. Okay, so that's the first evaluation. Minus plugging in pi over 4, we get pi over 4 plus 1/4 sine of, again, 4 times pi over 4 cancels the 4 and just leaves us with sine of pi now. And that ends that evaluation. Perfect. And then after we handle this, then we can multiply that result by 4, by 1/4, and we're good. Now, of course, if we distribute this negative, we will get, well, first off, sine of any multiple of pi, any integer multiple of pi, is 0. So that term actually doesn't need to be there. In fact, all we're really doing is doing 3 pi over 4 minus pi over 4, which is 2 pi over 4, which reduces to pi over 2. So our answer really is just 1/4 times pi over 2, which is indeed pi over 8. And if you did any other angles that enclose one loop, you'll get the same thing. And in fact, I kind of want to show you something. If you wanted to find the whole area, just use one full rotation, which is from 0 to 2 pi. Yeah, that works. I know it sounds a little weird, but in fact, I think going from 0 to pi will, I'm just trying to think how that works. But in any event, if you go from 0 to 2 pi, you'll actually get the same area. Well, you get all 4 areas, in fact. So let me just show that real quick. So if we find instead the integral from 1 over 2 cosine squared of 2 theta, which we know is just this. In fact, the integrand part is the same. But really what I'm saying is that if we change the limits of the integral from 0 to 2 pi, I know that sounds kind of confusing, but if you do this, you encapsulate the whole area, all 4 loops. And the beauty of this is that we still get the same antiderivative. In fact, the only things that change here are the limits. So really what we get, so if this is the same integrand, d theta, what you'll end up with is this same exact evaluation, actually. Now, since we're going from 0 to 2 pi, then this will be, well, 4 times 2 pi is 8 pi, that goes to 0. That's going to be 0, sine of 0, 0, so that still zeroes out. But now all we have really left is theta. So the only thing that doesn't zero out is theta, and we still have that 1/4 on the outside. So it's going to be 1/4 theta between 0 and 2 pi, which I know sounds a little bizarre, but that's actually what you'll get. Because, again, any multiple of sine, well, any multiple of pi plugged into sine will give you 0. So that's the reasoning why we don't need to write sine here. I'm kind of skipping some details, but I just want to show you something kind of cool that happens. So what you'll end up getting is this, 1/4 times, if you evaluate this by plugging in 2 pi minus plugging in 0, you just get 2 pi. And this, of course, is just pi over 2. Now, this is actually quite neat because, look, this, what we're saying here is that all 4 loops total to pi over 2. And if all 4 loops are indeed the same, then dividing pi over 2 by 4 will give you one of the loops, and look, that's it. Dividing pi over 2 by 4 will indeed give you pi over 8. So that's the one thing I wanted to show you that'll help solidify that idea that each of these leaves or loops, however you want to think of it, actually have the same area. All right. So now we're going to move on and we're going to do one more example. And this example, we'll see it'll be a little different. It's kind of the same, but it's a little different. It's where we'll have 2 curves and we'll have to find the area between, between the curves, so outside one and in the other. So let's take a look at that right now. All right, so for this example, we want to find the area of the region that lies inside the first curve and outside the second one. Without making this too complicated, let's kind of compare to what happens in Cartesian coordinates. So in Cartesian coordinates, you have a curve that's on top and a curve that's on the bottom. And let's just say they intersect. If they don't intersect, then we're given an x value point. So let me draw the bottom curve so that it intersects like this, and let's call that g. So to find the area between, what do? We take the integral of the top one minus the bottom one between the values a and b, where these represent the points of intersection. Now how we find a and b in this case is we actually set f equal to g and then solve for x. So that's exactly what we're going to do here to find the points of intersection. We're going to set this equation equal to that equation, so this r equal to that r, solve for theta. Hopefully we get 2 values. If we get more, then we have to kind of try to graph. In fact, you should honestly graph in general for basically anything polar. Graphing will give you that edge like I mentioned previously. So if you graph with the graphing utility, it'll only help. And I'll talk about graphing after the fact, but for right now, let's just do that. So to find the points of intersection, I'm going to set these equal to each other. We'll find the points of intersection which will represent our limits. The only issue now is that, well, which one's on top and which one's below. So if you remember for this, finding the area between curves, you can just guess if you don't want to graph, and then just take the absolute value. And that's kind of what we're going to do here, but it tells us inside this one and outside that one. So specifically what we're going to do is we're going to do this minus that. Now, the other thing too is that we're not just doing the integral of the function only, because of the Cartesian, area under the curve is just the integral of the function, but with polar, the area that's enclosed in the curve between 2 theta values is the integral of 1/2 r squared. So we need to use that integrand for each of them. So the area we want is, let me write A equals the integral between the 2 limits, which are the points of intersection, which I'll discuss in a bit, of the area formula integrand of each of these. So this one minus that one. So it's going to be 1/2 this r squared, which is 4 sine theta, minus 1/2 this r squared, which is 2 squared, and then d theta. Now before I find the points of intersection, we can actually deal with the integrand quite a bit here. So notice first off, 2 squared is 4, right there, and 4 over 2 is just 2, so this is going to be minus 2. Also, when you square each of these, you'll get 16 sine squared, like that. But then, of course, there's a 1/2 multiplied in front, so that'll actually be 8 sine squared. Also, to take the antiderivative of sine squared, we need to use a power reducing formula. So, in fact, let me write that over here just to remind us. So, sine squared of theta, if you recall, is 1/2 1 minus cosine of 2 theta. Perfect. Let me border this off a bit. And if you distribute this 1/2, and in fact, even before doing that, let's do this. We want to find 8 sine of theta. So if you multiply both sides of this equation by 8, we'll notice 8 goes, 8 divided by 2 is 4. Then distributing this 4 in, there we go, that's what I wanted to say. We'll get the 8 sine squared is really just 4 minus 4 cosine of 2 theta. Perfect. So this whole thing here is really 4 minus 4 cosine of 2 theta, and we still have this minus 2 lingering around. And then there's d theta, and then integral between limits. It's kind of being a little sloppy about it, but I'll rewrite it more formally in a bit once we deal with the limits. 4 minus 2 is 2, so there we go. This is actually pretty simplified. We have 2 minus 4 cosine of 2 theta, and we can actually, d theta, and we can actually antiderive this as is, but I want to now talk about what I've been holding off on, the points of intersection. So let's take a look. So let me write points of intersection like this. Is just, again, setting this r equation equal to that r equation. So if you write 4, and we border this off as well, 4 sine theta is equal to 2, just that r equals to that r equals. Well, divided by 4 will give you sine of theta is equal to 2 over 4, which is 1/2. And we all know sine is 1/2 at pi over 6. But if you recall the unit circle, and if you remember the acronym All Students Take Calculus, which will allow us to remember where sine is positive. Sine is positive here, A is all trig functions are positive in the first quadrant, and only sine and I guess its reciprocal cosecant are positive also in the second quadrant. So here and here, we'll get positive 1/2. They'll have the same reference angle in the first quadrant. Sine of pi over 6 is 1/2. And if this reference angle is pi over 6, that means this full angle will have to be, well, pi minus pi over 6, which is 5 pi over 6. Perfect. So that tells us that the theta values for which sine of theta is 1/2 actually happens at pi over 6 and 5 pi over 6, and there's only 2 of them here, so these will actually be our points of intersection. Great. So let me just fill in the blanks here then. This is actually 5 pi over 6, pi over 6. Same thing here, 5 pi over 6, pi over 6. Sorry about the small writing. And then 5 pi over 6, pi over 6. All right, cool. Now what? Let me just say before we move on. So remember in a previous example we saw, we had to write plus 2 pi k. That was only because it was 2 theta. So when you divide by 2, the 2 pi k divided by 2 becomes pi k, and that's actually meaningful in the interval 0 to 2 pi. But here, these are actually the only values. If you wrote plus 2 pi k and then wrote out the list of as many as you want and then narrow it down to be in between 0 and 2 pi, well, you'll find out these are really the only two anyways. So honestly, the only time you really need to write plus 2 pi k is if there's a number to be divided by in front of theta. That's really the only time. Anyways, I'm going to clean this up before we antiderive. You know, that's fine, actually. I'll antiderive first. Sorry for being so indecisive. But the antiderivative of 2 with respect to theta is 2 theta. The antiderivative of cosine of 2 theta, well, antiderivative of cosine is sine. Since it's of 2 theta, by chain rule, we have to divide by 2. And 4 divided by 2 is 2, so this is going to be minus 2 sine of 2 theta, actually, like that. And then evaluating this between our limits, pi over 6 and 5 pi over 6. Now, I think this is a good point to stop. I'm going to erase the board, rewrite this over here, and then continue. All right, so this is what we actually just found, where we left off at. And I'm just going to plug in the top one minus plug in the bottom one. So let's see. It's going to be 2 times 5 pi over 6 minus 2 sine of 2 theta. Well, 2 theta is double 5 pi over 6, which is 5 pi over 3. And you know what? It's funny because these 2 thetas are the same. So we actually notice this will also be 5 pi over 3. So remember when you double an angle, when you double any fraction for that matter, you just half the denominator. So that's really what I'm doing to get 5 pi over 6 to 5 pi over 3 when you multiply it by 2. Anyways, so that's the first evaluation here. And to get our second evaluation, well, we'll just plug in the bottom one. So 2 times pi over 6 is pi over 3, so it's minus pi over 3 minus 2 sine of pi over 3. Perfect. Awesome. So now what? Well, if we distribute this negative, we'll notice that this becomes negative and this becomes positive. So let me just change that to plus so we don't get confused with too many negative signs. So let's see. So this is going to be 5 pi over 3 minus 2 times sine of 5 pi over 3. Well, 5 pi over 3 is in the fourth quadrant. Sine is negative in the fourth quadrant from what we just saw with the unit circle. And as it turns out, any trig function of an angle, you just need to look at the reference angle after witnessing what sign it'll be from seeing what quadrant it's in. So really what I mean by this is we need to find the reference angle of 5 pi over 3 in the fourth quadrant. And in fact, this is the beauty, honestly, when it comes to radians. When you have an angle in radians, to find the reference angle, all you really need to do is just cover the number in front of pi on top. So really the reference angle is pi over 3. Sine of pi over 3 is radical 3 over 2, but since this angle is in the fourth quadrant, sine of that angle is negative radical 3 over 2. So there's a little bit of an explanation, but it gives you good insight, I hope. And then we get minus pi over 3 plus 2 times, well, sine of pi over 3 we just spoke of, that's just radical 3 over 2. Okay, great. Now there's a lot of cancellation that happens here. Notice the 2's cancel in each of these. Also the double negative is positive, so these actually combine. It really is just radical 3 plus radical 3, which is 2 radical 3. So let me write plus 2 radical 3. And then 5 pi over 3 minus pi over 3 is just 4 pi over 3. So there we go. That's really our answer here. 4 pi over 3 plus 2 radical 3. And I said I would graph this, so let me just remind us what these equations were. So I've kept the original equations here. And let me see if I can do justice and graph them appropriately. So let's start with r equals 2. r equals 2 is a circle of radius 2 centered at the origin. Okay, and you may have to take my word for the second one, but 4 sine theta is actually a circle above the x-axis with diameter 4. So it's going to have radius 2, so it's actually going to be basically the same circle, just above. So they overlap right here. Now, notice first off, they intersect at these angles, which actually do appear to be the angles we found, theta equals pi over 6 and theta equals 5 pi over 6. Now, it looks pretty fitting, of course, because, well, one's in the first quadrant and the other one's in the second quadrant. So that makes sense. Good. Now, this value we found represents the area that is in this 4 sine of theta curve, but outside of the r equals 2 curve. All right, good. Now, what you can do actually is you can find the area of the circle. Remember, area of the circle is pi r squared. Since the radius for each of these is 2, 2 squared is 4, so each of these circles will have area 4 pi. And you can actually compare that this number here, if you approximate, should be less than 4 pi. In fact, you can kind of see it makes sense that it's this portion of that circle. So just to compare to see that it kind of checks out intuitively anyways. There may be other geometrical ways of finding this area, but that would be specific to this setup. And it depends really in general on what polar curves you have. And this integral way of doing it is kind of the only way of doing it in general. It's the best way of doing it, in fact. Of course, you have to be given the equations. Anyways, with that said, that concludes this example, and now we'll move on to arc lengths. All right, so now for arc length, let us recall that what we learned from 10.2, I believe it was, for parametric curves, we can find the arc length. And in the context of polar, instead of t, this will be theta. So we can actually erase these t's with theta, and it'll be true within the context of polar, because polar curves are really just parametric curves where the parameter is theta instead of t. In fact, we could have actually used the area formula that we saw from parametric curves to derive the formula for the area for 10.4 that we saw today. The only thing is that doing that, it's really tricky and you need to use a lot of weird by parts manipulation, and it's easier for me to show that the way I showed it in this video. But anyways, let's move on and see what happens. So remember that here our x is equal to r cosine theta and our y is equal to r sine theta. Now the only real problem is that we need their derivatives, and we can find their derivatives, but you need, well, product rule for each of them. So if you take dx d theta, it's going to be, well, dr d theta times cosine of theta plus r times negative sine of theta. So let me change that to a negative. And again, that's because of product rule. Derivative of first, regular of the second, plus regular of the first times derivative of the second. But now for dy d theta, let's see what happens. So we need derivative of r, which is dr d theta, times regular of sine, plus regular of r times derivative of sine, which is cosine. So it's going to look a little nasty, but believe me, the integrand will actually clean up quite nicely. In fact, all I really want to clean up here is the radicand, the thing inside of inside of the radical. So if we square these, well, dx d theta squared, so let me write it like this in red. So if we square this is this whole thing squared, which we'll use actually a binomial property. It's a minus b all squared. Remember, that's a squared minus 2ab plus b squared. Similarly here, this will be a binomial square, but it's a plus b squared, so that'll be a squared plus 2ab plus b squared. And let's see what we get. And it's actually going to be quite nice. So we're going to get, the first one squared is dr d theta all squared times cosine squared plus 2 times the product of these, which will be minus 2 times, let me write it like this, r sine theta, cosine theta, and then we need a dr d theta. And then finally the last one squared is just plus r squared sine squared. Now this is just really the first term here. So let me just arrow that. And the second term I'll write below. So this whole thing plus this one I'll write down here. So let's see if we can do it. So again, that's going to be dy d theta squared, which is this one. It's going to be, well, this squared plus 2 times the product plus the last one squared. So it's going to be dr d theta all squared times sine squared plus 2 times these. So it's going to be, let me write it like this, r times sine of theta times cosine of theta times dr d theta. And maybe you can already start to see why this is so nice. And then plus the last one squared, r squared, cosine squared. Now why this is so nice, of course, is because, well, these two middle terms are the same, but they have opposite signs. So they actually cancel out. Also, r squared sine squared, that should be a square, plus r squared cosine squared. If you pull out r squared, you just get sine squared plus cosine squared, which we know is 1. So this will just amount to r squared, actually. Similarly for this one, if you pull out dr d theta all squared, you get cosine squared plus sine squared, which is also 1. So what this amounts to is nothing but dr d theta all squared. Awesome. So that's what the formula is actually, is just the length between these two theta values, let's call them alpha and beta, times the square root of, let me write it in opposite order. So I'll write this as r squared plus dr d theta squared, and then d theta. So this is the arc length formula. But again, keep in mind here we want to go from smaller theta value to a larger theta value. So here we want theta to be in between alpha and beta like this, and we want these alpha and beta values to be in between 0 and 2 pi when we can. So let me asterisk that, because we know what that means. Sometimes you have to dip outside of it. Sometimes you have to either be larger than 2 pi or less than 0, but we've seen examples of those already. Now, to be quite honest, the examples that you'll see, or the homework problems rather, that you'll see in the book, will be fairly straightforward for lengths. They'll already basically give you the bounds. So we'll do, I think we'll just do one example. I think that'll be okay for this, because this, I think, is more straightforward than our area was. So anyways, let's take a look at that example now, and that'll be it for this video. All right, so I said I would do one example, but it's a two-parter, so I kind of cheated. It's really 2 examples. But anyways, we want to find the exact length of each polar curve, and I've written here the arc length formula that we've just discovered. So let's take a look now. So here I'm going to have the length is equal to the integral from 0 to 2 pi, that's just the bounds here, 0 and pi, sorry, not 2 pi, pi, of the square root of what? The square root of r squared, so this whole thing squared is just 2 squared cosine squared, so that's 4 cosine squared. And then we'll need plus dr d theta squared. Now what is the derivative of 2 cosine? Derivative of 2 cosine is, well, 2 sine. Squaring that will be 4 sine squared, and then d theta. Now this is pretty simple to do because, of course, we'll notice that they all have 4 in common. Pulling that out, we'll get cosine squared plus sine squared, which is 1. So this is really just 4 inside of the radical. And of course, the square root of 4 is just 2, and you can even pull that out of the integral because it's a constant. And then we're kind of done, because of course the integral from 0 to pi of d theta, in fact, the integral from a to b of d whatever, is always just top minus bottom. So this is just 2 times theta minus 0, which is just 2 pi, which is kind of curious. No, yeah, that makes sense. So I was thinking of something else. But if you actually graph this, you'll see this is just a circle. So the circle will have radius 2 actually. In fact, let me just draw for you. It looks like this. Or this is 2. Now, of course, the circumference of a circle of radius, it's radius 1, diameter 2. But circumference of a circle of radius 1 is just 2 pi. Now, that sounds a little confusing because if you go from 0 to pi, you're only covering the top half. But as it turns out, for cosine of theta, 2 times cosine of theta specifically, well, when you plug in pi, you get negative 2, so the radius is negative 2. So if you go here, you're actually back down there. So in reality, it draws the full circle with only theta values from 0 to pi, so that's a little funny. So that may throw you off a little bit, but if you kind of graph and create with the table, you'll see what I mean. But most people won't really care. They'll just be happy with this answer. So I'm not going to graph for the next one. I'm just going to go on. And let's see. So the setup will be, again, length equals the integral from lower bound to upper bound, so 0 to 2 pi, of the square root of r squared. R squared is theta squared squared, so that's theta to the fourth, plus the derivative. Derivative of theta squared is just 2 theta. If you square that, you get 4 theta squared. Now this integral is not honestly very difficult to do, but you have to recognize something first, and without recognizing that, it's a little difficult to do. So the only way I can see to do this is by factoring theta squared out. When you factor theta squared out, you get theta squared plus 4 on the inside. Now, of course, the square root of theta squared is theta, so in reality, this is the integral of theta times the square root of this theta squared plus 4 d theta. Let me kind of make a border here. And then again, our limits are 0 to 2 pi. Now, this becomes a little more simple because what comes to mind should be u substitution. So if the inside is u, then let's see. So u is going to be theta squared plus 4. Good. So what's du? du is going to be 2 theta, 4 goes to 0, d theta. We have theta d theta, so we can divide by 2 to get 1/2 du is going to be replaced, well, it's going to replace theta d theta. Great. So let me box this so it doesn't get in our way. We'll have to change some limits here. We may need to erase for space, but that's to be seen. Let's see. So now we have the integral. I'll change the limits in a second. The theta d theta is replaced with 1/2 du, so I'll pull the 1/2 outside of the integral, of course, because it's a constant. And it'll have du, and it'll have u, well, square root of u. But I'm going to write it as u to the 1/2, so we can antiderive more easily. And now the antiderivative of u to the 1/2 is u to the 1/2 plus 1, which is u to the 3/2, divided by 3/2, but dividing by a fraction, we'll just multiply by the reciprocal of 3/2, which is 2/3, and then evaluate between the limits that we still haven't found yet. And the nice thing here is there's this cancellation of 2's, here and here. And now let's see if we can find out what these new limits are. So when we plug in 0, we get 0 squared plus 4, which is just 4. So that'll be our bottom limit, I guess. Let's write it like this. It's 4 on the bottom. And then if we plug in 2 pi, then on top we'll get, it's kind of weird, but it's 2 pi all squared, which is 4 pi squared plus 4. So I'll write it like this, 4 outside of pi squared plus 1. I'm just factoring it really. So on the bottom we'll have 4, on the top we'll have 4 outside of theta, pi squared, plus 1. Pi squared plus 1, but that 4 is on the outside. There we go. Right, so now this is 1/3, and then let's do our evaluation. So we're going to take the top one to the 3/2. By the way, 4 to the 3/2 is just going to be 8, because 4 to the 1/2 means square root of 4, which is 2, and then 2 to the 3rd is 8. So you can try that on your own, but that's what you'll get. And then times pi squared plus 1 to the 3/2. Let me write it like this. Okay, and then minus 4 to the 3/2, we already said 4 to the 3/2 is just 8. And in fact, if we pull out this 8, we'll be left with 8 over 3 outside of pi squared plus 1 all to the 3/2, and then minus 1. Brilliant. Nice. So we actually didn't need to erase for space. Great. Awesome. So that's all I'm going to say for areas and lengths. So that's really it for 10.4. So I'll see you in the next video for 10.5. It's going to be interesting, to say the least. It's not really related to calculus. It's really an intro to build up 10.6. So yeah, this class, by the way, will not cover 10.6, but you know, if you're watching this video and you're taking a class that does cover 10.6, then it'll actually be good use. Otherwise, it's a little out of place. But in any event, we'll still cover the material. So I'll see you then. Thanks for watching.